So in the previous topology video, we discussed the notion of an order relation. An order relation on a set is a relation that satisfies three conditions, namely comparability, non-reflexivity and transitivity. So let us now next see this next definition based on that notion. Let X be a set, this be an order relation on X. And we can continue. Actually, there is one more thing to consider, which is this pair of elements such that A is related to B. If you want, you can say A is less than B, while at the same time keeping in mind that this is not our ordinary less than relation that we have in the set of real numbers, for example. That's because the objects in the set X may not be numbers. They may in fact be vectors or functions, something else also they may be. So this is a general order relation. We define the open interval A comma B in X as this. It is the set of those elements in X which are related to A and B like this. So this is exactly the definition of open intervals that we have in the system of real numbers. But the exact same thing we can consider here also in any ordered set. And there is more to this definition. If this is empty. Now we don't normally see means we never see this thing if A and B are real numbers and this is our ordinary less than relation. Then this never happens. Between two distinct real numbers, there is always another real number. But in a general ordered set, this may happen. If this happens, then A is called an immediate predecessor of B and B is called an immediate successor of A. More simply saying, if this is the case, then the element next to A and larger than A is B. Such an element exists and it is B. And the element next to B, just the one smaller than B, is A. In the system of real numbers, this is not possible, but in many other systems it is possible. In fact, if you think of the ordered set of natural numbers, or more accurately positive integers, in this book we do not assume 0 to be a natural number. It's just a matter of convention. Okay. So on this set, if you consider the ordinary less than relation, then this becomes an ordered set with that relation, there, for example, this open interval really is empty. That's because there is no natural number that is strictly greater than 1 and strictly less than 2. And that is why 1 is the immediate predecessor of 2, the element that comes before 2, and 2 is the immediate successor of 1, the element that comes just after 1. Okay, so you can consider this example. Somewhat loosely speaking, ordered sets which are discrete like this, one element, then next element, something like that, there you have immediate predecessor, successor, but ordered set which are like a continuum, like the real line, their elements do not necessarily have immediate predecessor or successor. Okay, I am saying these things in a very vague manner without saying what a continuum means or what a discrete set means, but you get my point. All right. Now next we are going to see another notion which will remind us of the idea of isomorphism from algebra. When do we say that two groups are isomorphic? When there is a bijection between them which preserves the algebraic structures of the groups or the operations. A similar idea is present here, but which will preserve now the order structure between two ordered sets. Let A and B be sets with ordered relations this and this respectively. Okay, so we are having two ordered sets. This is the ordered relation on A and this is the ordered relation on B. In order to distinguish them, we have written A and B as suffixes. We say that A and B have the same order type if there is a bijection. It's like saying that two groups are isomorphic if there is a bijection which also preserves the binary operations. Here also there is a bijection f from A to B which preserves order, but preserves order means what? Or like this also we can say, or F is order preserving, and what that means is this: for any two elements A1 and A2 in the domain ordered set A, this implication is true. If A1 is less than A2 in the ordered set A, of course, so we are using the ordered relation that we have on A. Then the image of A1 and the image of A2 under F are related by the order relation on B like that. More simply saying, if A1 is less than A2, then f of A1 is also less than f of A2. In that sense, f is order preserving. So, if such a bijection, an order preserving bijection exists between two ordered sets, then we say that they are of the same order type. Or as ordered sets, there is no distinction between them. They are order isomorphic, which you already know what this means and what interpretation you can have of this. It simply means that as ordered sets, A and B are actually the same thing. They are like isomorphic groups, only isomorphic ordered sets. So whatever happens in one ordered set, which involves the order, an exactly similar thing will happen in the other ordered set as well, with respect to its own order, and conversely, vice versa. Okay, so this is the notion of ordered sets. Now let us see two examples. According to the numbering scheme that we are following, this is example 9. Do you remember in example 8 we considered that blood relation, sibling relation, that thing, that was example 8. The ordered sets -1, 1 and R, where we are not saying what the order relations are because it's understood that our R has the usual strict less than order on it, and this is just that order but restricted on the subset. So technically we are looking at two ordered sets. They have the same order type. Why? It can be proved that the function f from -1, 1 to R defined by this rule x divided by 1 minus x square is an order preserving bijection. Now we will prove this in exercise 9. When we start solving the exercises, there you will see a proof of this fact. Right now, however, we won't do it. The next example, which also gives us two ordered sets of the same order type, there we will prove that they have the same order type. Oh, but before we leave this example, we can at least see how the graph of this function looks. Let's just see that. That will give us a rough idea of why this is true. The graph is going to look like this. say this is our interval so this is our interval minus 1 comma 1. So what we do, we draw perpendicular dashed lines passing through these real numbers minus 1 and 1. These of course are not parts of the graph. These serve the purpose of showing us in which region the graph lies. The graph is somewhat like this, something like this, where you can understand that as you go lower and lower, this portion of the graph becomes closer and closer to this dashed line, but it never touches it, nor crosses it and goes to the other side. Similarly, on this side, if you go higher and higher, this portion of the graph becomes closer and closer to that dashed line without ever touching it. You can see one more thing also. We have, what is this? This is a rational function, right? A quotient of two polynomials, and such functions are well defined provided the denominator never becomes 0. Is there any possibility for this to be 0? Well, there are two real numbers which if you put in place of x, it will be 0, and they are minus 1 and 1. However, minus 1 and 1 lie outside the domain, and that's why there is no problem. This is a well-defined function, and its graph happens to look like this. So you can appreciate why this should be order preserving just by looking at the graph. Say you take 2 points A1 and A2 in the domain of F. That means here. Say A1 is negative and A2 is positive. Then what are the corresponding F values? This is F of A1. This point is F of A1 on the y-axis, and similarly you can find F of A2. This is F of A2. A1 is less than A2 in this ordered set. F of A1 is less than F of A2 in this ordered set, which is R. This real line is R. I mean, it's geometrically it's R. So it's because that the graph is going like this. You can roughly see that this is going to happen with any pair of points. That is why it's order preserving. Moreover, its increasing nature tells us that it will be 1 to 1. For for any point on the real line, there cannot be two inputs for which it's an output. That comes from the increasing nature of the function. And at the same time, it's onto as well. You can see from the graph. Any point you take, whether it's really very high or low or goes below the x-axis, no matter what point you take in R, there is a corresponding point on the graph. And from that point, if you draw a perpendicular to the x-axis, you will get the input for which that point is the output. Geometrically, these are just some vague ways of seeing why the function should be order preserving and why it should be a bijection. But of course, when we solve this exercise, we will do these things rigorously. Let us next see example 10. consider the ordered sets union the open interval 1 comma 2 and the closed open interval 0 comma 1. Oh, and ordered sets means if something like this is simply given without saying what the orders are, then you have to assume that they have the order taken from the ordered set of real numbers because they are subsets of that ordered set. If a set is a subset of a non-ordered set and nothing else is said, you have to assume that the order of this subset comes from that ordered set. Now these two sets have the same order type. They have the same order type, and we will now show this. Define a function f from a to this by this rule. F of x is 0 if x is equal to 0 and x minus 1 if x lies in this portion of A, that is this. Whenever you define a function, the first thing you have to see is that the function is well defined. That has two aspects. The first is that for any point in the domain, the output should lie in that second set, which some people call codomain, some call range. Okay, so in order to not go into that thing, we call it the second set. And the second aspect is that for your chosen point, the output should be unique. So let us first see if we do get the outputs in this second set. If my input is 0, the output is also 0, which is present here. Okay, fine. If my input is, however, coming from this portion of the domain, then my input x looks like this. And the output, according to this rule, is x minus 1. What can we say about x minus 1 from these inequalities? If you subtract 1 throughout from all the terms, you get 0 less than x minus 1 less than 1, or x minus 1 belongs to 0 comma 1. Fine. Obviously, this is a subset of this, x minus 1 lies here. Okay. Is there any possibility for having two outputs for a given single input? No. If your input is 0, output is 0, nothing else. That's what the function says. Again, if your input x is lying here, then the output is x minus 1, it's nothing else, and x minus 1 is a single real number for a given x. That is why the function is well defined. We don't, of course, write all these things. We simply write like this. Clearly, f is well defined. If it's really very easy to see that the given function is well defined, we don't even mention it. We don't even write this line. We straight away start working with this function. But always keep in mind that whenever you do so, you have to first of all make sure that your function is well defined. Okay, so next what do we do? Next let us show that the function is a bijection. It is both one-to-one as well as onto. So let's show the one-to-one thing first. Let A and B be two elements in A such that f of A is equal to f of B. Our aim is to show that A and B are equal. If you have equal outputs, then you should have equal inputs as well. That is one-to-oneness. If A is equal to 0, then f of A is also 0. But then that is also equal to f of B. Our aim is to prove that B is also 0 now. What will go wrong if B is not 0? If B is not equal to 0, then since B after all is coming from A, so if it is not 0, then it should lie between 1 and 2 because that is what A is. But then 0 is less than x minus 1. Oh, sorry, it's not x, it's B. That's what happens when something, you have written something wrong. Did you notice me hesitating? Because suddenly I just wrote x here and then I got confused because it's about B. No. So this feeling should be there. It should not be that you just wrote anything and you keep on going. If you have done something wrong, immediately it should click, no, something is wrong. But then what are we getting? F of B is greater than 0. So that is clashing with this thing. This is a contradiction. That means B cannot be non-zero. Thus B also has to be equal to 0. So in this case where A is 0, B also has to be 0. Similarly, if B is 0, then A must also be 0. So in the case where at least one of them is 0, the other one is also 0, and so they are equal. Now, let both A and B be non-zero. So if both of them are non-zero, then we know what is f of A. It is A minus 1 and f of B is B minus 1. So A minus 1 is equal to B minus 1, which again implies that A is equal to B. So in any case, if f of A and f of B are equal, then A and B have to be equal. Hence, f is 1 to 1. Next comes ontoness. For ontoness, we take any element in the second set, closed open interval 0, 1. Let y belong to 0, 1. If y is equal to 0, then f of 0 is y. So we get a pre-image or inverse image for y if y is 0. If y, however, belongs to 0, 1, then this, and so adding 1 throughout, you get 1 less than y plus 1 less than 2. In other words, the real number y plus 1 belongs to the set capital A, because recall that A is the union of the singleton set 0 and the open interval 1, 2. Thus, y plus 1 belongs to A. Also, what is f of y plus 1? Since y plus 1 is not equal to 0, so by the definition of f, this is y plus 1 minus 1, which is equal to y. So in this case also, we have found an inverse image for y under f, which is y plus 1. So every element in this set is an output for some input under the function f. Hence, f is onto. So we have shown that f is indeed a bijection. Next, we still have to show that it's order preserving. For that, let A1 and A2 be two elements in A such that A1 is less than A2. If you want, you can write capital A here as suffix to denote the ordered relation, but because the two ordered relations on the two sets are coming from that same source, which is the ordered relation on R, so basically they are the same thing. That's why we simply write less than. Okay, now if A1 is equal to 0, keep in mind that 0 is the smallest element in A, because the other elements lie between 1 and 2. So it's possible that A1 can be 0. It's possible for A1 to be 0. That is one case. Then f of A1 is also 0. Also, now see, A2 simultaneously cannot be 0 because A2 is greater than A1. So A2 lies between 1 and 2. That's the other part of the set A. A2 has to lie there. And so, subtracting 1 throughout, you get this. That is, f of A1, which is 0, is less than f of A2. So in this special case where A1 is 0, we have been able to show that f preserves order. Now let A1 be also not 0, then it will be greater than 0. Now both A1 and A2 will lie in that open interval 1, 2 in A, which is the part of A. Then A1 minus 1 is less than A2 minus 1. You can subtract 1 from both these terms and have the inequality intact. I mean, its direction intact. It doesn't get flipped. I.e., But because a1 and a2 are now both different from 0, so by our definition of the function f, a1 minus 1 is f of a1 and a2 minus 1 is f of a2. So in this other case also, f preserves order. Thus, f is order preserving. And that is why the two sets have the same order type. Okay, now a question for you. Did you see that we had to do three things? We had to prove that f is 1 to 1, f is onto, and f is order preserving. Is it enough to simply show that f is order preserving and onto? Does 1 to 1ness of f follow immediately from the fact that f is order preserving? If so, why? If not, why? Just think about it, okay? After this, we have a very special type of order relation after all, but a type of order relation which you can define on a Cartesian product of two ordered sets. It's called the dictionary order relation. We will discuss this and then we will discuss other things also which are there in this section, but in the next video on topology. So that will be all for tonight. See you in the next upload, whatever that is. Until then, this is me, Lucifer, from a mathematical room. Have a nice day.